Today we are going to discuss three technologies which are prominent these days, which you hear in the news. Some of you know about them, and I'm going to describe how they are converging together into one single point. So these three technologies are the semiconductor one, the one which you all hear about these days is AI, and the third one is quantum computing. We will discuss the evolution and maturing of the semiconductor technology. Then we will talk about the progress in AI, and finally about why quantum computers are required, why they are important, and what class of problems they are ready to solve. So, if you start with the beginning, those of you who are in physics and in engineering field, you would know that the transistor was discovered way back in 1947. And before that, in fact, that idea of a semiconductor device was coined by Julius Leidenfield in 1926. And thanks to the works of physicists, ever since then, we today have what we call computers. We have all the chips, which are very advanced. Most of us know about that. These days, we have semiconductor technologies where a chip can consist as many as 100 billion transistors, for example. The semiconductor technology is really based on silicon, and silicon atoms are a specific type of atoms where they allow you to either create a conductor or an insulator based on the voltage that you apply. So, it is that is why this element was chosen, and one good aspect of silicon is it is available everywhere. In nature, you see it is in the sand, on the seashores, in beaches, and there is no shortage of silicon. So, this is why this technology is something that can flourish with very little I would say material cost for this. Okay, there is obviously a technology cost to create the advanced level of semiconductor, but this is an important element to remember. There are two types of semiconductors we know. There are p type and n type. Those in physics background would know already what they are. P type are where there is a net positive charge which carries the information. N type where there is a net negative charge, just like electrons carrying the information, basically current. The field effect transistor was invented, was an advanced version of the original transistor, and that was the MOSFET really came about sometime in 1959. The idea of MOSFET was it's easy to miniaturize. In the beginning, you had a single transistor which was like a size of this big, something you could see in your hand, for example, like a thumb size. Today, the field effect transistor back in 1959, when that was created, we realized that can be actually miniaturized. You can start shrinking the size of those transistors, and as a result, you can put more and more transistors into a chip, which is called a chip today. And so you can have higher packaging density, for example, and as a result, you can have even lower cost because the size is small and it is scalable. Now, until the first decade of 21st century, we were able to scale this all the way up to billions of transistors. But then somewhere around 2000, we got our first gigahertz processor. We all know that AMD's Athlon was one of the gigahertz processors. 2005, we had multi-core CPUs. Some of you remember that. We started having a single core, just single CPU. Then you said a 2-core, quad-core, hexa-core. Now you have 8-core, and you got multi-core processors these days. Then in 2008, we crossed the billion transistor count for a microprocessor, and then that one was Intel 6-core Xeon 7400 processor, and that used a 45 nanometer process technology. What is that? The 45 nanometer process technology is essentially, you can think of a size of the transistor in some sense. The 45 nanometer, most of us know, is the one part in a billion of a meter, and the 45 of those will form a transistor, and that's kind of a width of the transistor in some sense. It also allowed us to voltage scaling. So, in the beginning you needed a higher voltage to perform these technology to activate these transistors, and with the field effect transistor you could actually start lowering the voltage level as well. After that, while this was happening, we hit a roadblock. So, what was the roadblock? The roadblock was, some of you might remember, we started talking about multi-core and then we don't increase the frequency anymore. You don't hear 10 gigahertz processor, you don't hear 20 gigahertz processors. You started hearing 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, and then suddenly nobody is talking about gigahertz anymore. The reason being the power consumption in a chip is square of the frequency. So it will start getting hotter and hotter. It can actually melt the chip. So you stop, you cannot have more frequency. But then how do you make more powerful transistor? Well, the only way to do that is to shrink the size of the transistor, so you can have more number of transistors inside in the chip. So that's where we got into, and then we also had some other physical effects into the chip, which is like short channel effects, leakage currents, process variability, and mobility degradation. All this kind of technical jargon you can think of. But the idea is that these were the roadblocks which are not allowing us to have a processor with the FET technology, with the feed effect transistor technology for too long. So then what happened after that? Then came what we today call as a 3D transistors. The 3D transistor, unlike the FET field effect transistors, were in a plane. So you had a channel created in the single plane. The 3D transistors where the channel became like a vertical one. So you had the channel going like this, and then on top, and then going down. So you had something like in 3 dimension. What's the idea in that? The idea is that if you increase the third dimension, if you have a third dimension, you can actually have the bigger channel, and then you can have more current flowing through the system, through the same channel. As a result, you get more powerful computers. For example, you can have more current. That means you can do more computing. You can have more processing power for this chip. So 3D transistors back in 2011, they were created at that time by Intel, and then it went on for a while. For about a decade or so, this was going pretty well. Then in 2021, we had another roadblock. So what was the roadblock? So first of all, we obviously needed to have more. The demand for higher performing transistors is always there. There is never a shortage for that. And you also wanted better electrostatics behavior of these transistors, lesser power consumption, as I told you earlier too, and even more drive current. I told you that drive current increases when you use 3D transistors, because now you have more electrons flowing through this, because the net resistance is less. As those of you in physics and engineering background, when you have lesser resistance for the given voltage, you have more current. So the more current, but we wanted even more current than that. So what do? You cannot really use these 3D transistors anymore, and you obviously wanted more number of transistors in the single chip. So you started with what is known as this GAA. This is the technology of today. So GAA is gate all around. So where the channel is really surrounded by the gate around the whole channel. So it's just a 3D with it's kind of it's a 3D plus the third dimension is really going all around the channel. So channel is surrounded by the gate layer, and as a result, what you get is even lower voltage. So that means you can now. Why do we need lower voltage? Because the power is proportional to voltage. If you have lower voltage, you can reduce the power consumption. That means the chip will not get hot anymore. You don't need to put fan in the computer, and you can have 35% lower area with this technology. The lower area means you can pack more transistors into this chip again, and obviously you have increased drive current, because as I said, there is a gate all around, so more channel width, and as a result more current. And then you also have use what's called the nano sheets instead of nanowires here. So for example, there are two technologies here. There is a nanowires and nano sheets. Nanowires were kind of wires at the very, very fine scale in some sense you can think of, but that technology is very, very difficult to make. So it was decided that Samsung Semiconductor is the one which actually uses nano sheets to create the channels, and that technology has been working since 2022. This is a 3 nanometer. Now remember earlier I told you about 45 nanometer, that was back then. 3 nanometer is essentially 30 hydrogen atoms in some sense you can think of. A single hydrogen atom is about an angstrom. So 3 nanometer would be 30 hydrogen atoms lined up in a single row. It's a pretty small size for the transistor. Now when I say 3 nanometer these days, this nanometer doesn't directly translate to the size or the width of the transistor, but you can say in some sense it does scale accordingly. So that means the feature size somewhere is about 3 nanometer today. Okay. So Samsung came up with this technology and they call it MBC FET, which is a multi-bridge channel field effect transistor. It's still a FET, field effect transistor. A field effect transistor is one where you apply the field, which is voltage, and the current starts flowing. You call it the field effect transistor. Now similar to this, Intel has its own version of GAA and they called it ribbon FET, which is something similar. It's like again nanosheets, gate all around, and you have a transistor built in that. You can have multiple nanosheets, because you have more nanosheets, you can have more channels, and more channels means you can pump more current. That means you have more drive strength. So that's the beauty of this new technology. This is where we are today. Now Intel also has something called a power VIA. I'm not going to go into this because this is highly technical in this case. But this is just a picture that you see today right now, and this tells you the evolution of this semiconductor process. So it started with all the way from 3 micron back in 1998, 97 time, 1988, 87 times, and then you had somewhere around that 45 nanometer was around 2007. And today in 2022-23 we are talking about 3 nanometer, 2 nanometer technology. That's where the semiconductor technology is. Who are the leaders in the world today in this technology? Taiwan Semiconductor. Taiwan Semiconductor actually builds world's largest number of most advanced processors. Okay, so they hold Taiwan as a country holds about 64% or 65% of world market in manufacturing these chips. Samsung Semiconductor on the other hand has about 17% of world market. Global Foundries of the United States has about 7%. Rest of the world is, you can think of about rest 10-15% is the rest of the world combined, which includes the rest of United States, Europe, and South Asia, if there is any there. I'm talking about advanced technology. Behind all of this technology is one single company in the world. It's called ASML, Advanced Semiconductor Materials Lithography Technique. And this is this machine engineering is a marvel of human engineering, because no other company in the world either knows how to make this or can make this. This single company sends its machine to either South Korea, to Samsung, or to Taiwan to build their chips. So while it is manufactured in those countries, the actual machine which does all this work behind the scene actually comes from Netherlands. So what did it all give us? Like, we had all this technology behind us. What do we get out of this? We get out of this some of these world's fastest supercomputers. We have exascale supercomputer today, Aurora and Frontier, and its computing power is about 1.1 exaflops. If you don't know what an exaflop is, you know what a megaflop is, million floating point operations per second. Gigaflop will be a billion floating point operation per second. Then you have teraflops, which is a 1,000 billion operations per second. And then you have petaflops, which is a 1 million billion flops. And then you have exaflop, multiply that by 1,000 again. So you can imagine the enormous amount of computing power this semiconductor technology has given us today. What do we use these things for? Everything from pure research into medicine, research into space, research into nuclear simulations, for all the nuclear technology, and you name it. New material discoveries, they all come from this. However, CPUs or the microprocessors are not really what we use in what we call today AI. So now I'm transitioning from semiconductor into the AI world. So why did GPUs become more powerful? Why did they become more used than the CPUs? The difference between a CPU, which is called a central processing unit, which is like a general purpose microprocessor. GPUs are purely designed for graphical processing. Now those of you who are game savvy, to play video games, you need a good graphics card to play a good video game in 3 dimension. Right, with the good lighting effects, good all these 3-dimensional objects playing around, running around, killing each other or doing whatever fighting. So those are that's a graphic processing. Now math students would know a graphic 3D modeling is nothing but ray tracing. It's really a ray diagram, ray tracing, and all that requires is a vector processing with matrices. So vectors and matrices. It's really a simple linear algebra problem. So the entire graphical video games is really a linear algebra problem. That's all it is. Now what do we need linear algebra for? matrix multiplication, matrix addition, subtraction, whatever, and inversion probably as once in a while, and then multiplication with vectors, which are again matrix with a single column. So you have all of that, and all of that GPUs are very good at. So why did they become more useful for AI? They became more useful for AI because AI uses again linear algebra. That's all it really uses. As for models, for the generative AI foundation models, most of the work is done using linear algebra, matrix processing and things like that. GPUs were their choice because CPU is just too much. It's like using a car to go 20 feet of a distance. You probably need a bicycle, maybe even you can just walk. So you don't need more complex chips to do what when your work is very limited in scope. GPUs were designed for that. Another beauty of GPUs is, unlike a CPU, unlike a central processing unit or a microprocessor, which cannot do parallel processing, it can probably do 1 or 4 or maybe 8 processes in parallel. A GPU can do hundreds of thousands of processes together. In fact, sometimes some of these most powerful GPUs can do millions of processes together, like in parallel. So they are like a parallel computers running, doing your job, and that's why they took over the world. For the last 3-4 years, ever since ChatGPT announced their generative AI model, we all hear about, or OpenAI announced the ChatGPT, people got interested into this area, but the work was already done. All the modeling, all the foundation models for the generative AI were created using these graphical processes. That's why NVIDIA as a company, which was so small compared to Intel, which was the what you call as the father of microprocessors for God knows 30-40 years, Intel is no longer anywhere close to where NVIDIA is. In terms of world capitalization today, NVIDIA is number 2 company in the world in terms of market value, and Intel is way down. People don't even hear. It's a 30 plus times more market capitalization than NVIDIA has, purely for this reason, because AI has taken over most of the world now. Now, NVIDIA created this extremely powerful GPU. It's called Blackwell GPUs and one Grace CPU combined into one single unit, and that can do almost 208 billion. It has 208 billion transistors, by the way, even more than the CPU generally has, and it can do 1.4 exaflops of AI performance. Now think about this. I showed you earlier the supercomputers, 2 supercomputers, the Aurora and Frontier. They had 1.1 exaflop computing power. It was like a big building where these computers were housed, and they have imagine amount of power that you need to run those. Compared to that, this is a single box from NVIDIA using GB200 NVL72 graphical processors, and they are able to give you a computing power of 1.4 exaflops, but they explicitly say it's AI performance. Why? Because AI only needs, as I told you earlier, linear algebra, matrix multiplications, matrix processing, and that's all really we care about. So if the AI models care about just that, why would they use something else? This is much smaller in size and gives you much higher performance than even a supercomputer, much easier to maintain. So that's where this technology is today. So that's why all of the world's, most of, I would say not all, but most of the world's work happens, AI work happens behind the scene using GPUs, not CPUs. So with this much power that you are getting, so who really needs this? Like, how much computing do we really need? Like, this looks like forever, there's no ending to this. So who will use and how much computing power really your AI models need? I've given you an example of these 4 AI models. Let's look at GPT-3. Everybody is aware of GPT. ChatGPT was based on the GPT-3 models. For example, 2020 is when they had this trained. It used 314 million petaflops. That's the 314,000 exaflops of computing. Obviously, no single computer can give you that, but that means you have to run these things for days and months. So in fact, many of these AI models, GPT-3 AI model, AlphaGo AI model, Minerva AI model in 2022 used 2.7 billion petaflops of computing. So that gives you an idea that there is a never ending thrust, thrust for more and more computing power for these AIs. So now this next question comes is, do we really have, like, are we going in the right direction? Like, will it ever provide so called sufficient amount of computing power? We'll come to that a little bit later. But before that, I just want to go into one quick thing in AI. There's a lot of confusion among people about what AI is. So there are three important aspects of AI. What we know AI as today is really what is called ANI, artificial narrow intelligence, and it's also called weak AI in scientific community. What it really means is that your AI is able to do a specific task in a very fast way compared to, say, human beings. Okay, but it cannot do all the tasks together. Like, as a human being, I can do everything. I can do cooking, I can wash my clothes, I can go run around, do help somebody, drive the car, maybe fly the plane, fly a rocket, everything. I can do everything as a human being. My brain has lots of capabilities. AI today cannot do all of that. AI can do good. AI can run a car. You can have cars which run automatically, self-driven cars. But that same AI model will not be able to cook food for you, for example. You need a separate AI model for that, or cannot bring groceries for you from outside. So when you have those kind of models, those kind of AI models, then you need to have a kind of bunch of models differently to get combined together, and so it can do multiple tasks together. So that's where came with generative AI. The Gen AI that you know today, ChatGPT, for example, it can do multiple tasks. So it can do, for example, it's the language processing. It's based on the large language models, where it is looking at, say, images, pictures, or videos, or text, or maybe sound, and then it can generate data. But still, all of that is related to what you call language processing today. We still don't have AI models for, in the single machine as AI model which can do many other tasks combined together. So once that happens, we'll call it as AGI, artificial general intelligence. And as a definition, you can think of it this way: artificial general intelligence will be something where if I put a machine here behind a screen and a human being here behind the screen, and I ask them, like, say, 10,000 questions about anything. About a joke, I crack a joke, I want to see who is smiling, who is laughing, do they understand joke or not, or ask any number of questions. If at the end of this whole experiment you are not able to distinguish between who is a human being behind which screen is a human being, behind which screen is a machine, that's the age when we call that we have reached AGI, artificial general intelligence. Now, there is a lot of debate in industry about whether or not we have reached here. Some people think we are going to be there, for example, in next 5 to 10 years. Elon Musk thinks it's very close. Now, some people think no, it's never possible, but there is always a debate. Now, this is something you want to keep track of. ASI is the ultimate version of AGI, where, remember, from ANI, artificial narrow intelligence, to AGI, artificial general intelligence, we as human beings are making those machines. We are helping them doing all of these things. But what's the issue there? Humans are very slow in everything. Our response time is extremely slow. The best human being probably can respond within few milliseconds, maybe. That's it. Machines can work at microsecond, nanosecond time scales. They can work extremely fast. So once you reach AGI, AGI can do its own everything. It doesn't need to listen to human being anymore, for example. You might be able to train it to do that, but once it has its own intelligence, then it doesn't need to listen if it doesn't want to. And then from AGI to ASI, which is artificial superintelligence, that path will be exponential, because then the machines are taking over. Human beings are not involved anymore, and machines can do things exponentially faster compared to humans do. And that's one of the beauty of this, well, plus or minus both, I would say, that it could be dangerous for humans, or it could be useful depending on how you have trained these things to start with. Or in some cases, you probably don't even have a choice here. Now, some of the things that you might want to know about foundation models is that they are basically the mathematical models which are at the foundation of all the generative AI. Okay, there is a large language model, that's all we know about today, ChatGPT kind of stuff. And by the way, when I say language, it's not just a language of speaking like English or Hindi or any other spoken language in the world. It also includes computer programming languages, for example. Today you can ask ChatGPT or any of these GPTs, the generative pre-trained transformers. You can ask them whether, like any question, okay, write me a program which does this, this. And it will give you a computer program in any language you want, almost 100 plus languages, in matter of seconds. We don't need programmers anymore to do all that kind of work. So that is actually already available today. You can work with GPT to test some of these things out. One of the biggest issues with the AI right now that is available today is the trust issues, the transparency, and the slow lawmaking and regulations. So what's the trust issue? Trust issue is, remember OpenAI's ChatGPT was trained based on the internet data, and as all of us know, there is a lot of misinformation, disinformation, and all kinds of garbage in the internet, apart from good information as well. The question is, how does the machine know what is right, what is wrong? On top of that, we have what is called our own biases in it. Some of them are our subconscious biases. We are not even aware that we are biased on something. So those things are also built into the way humans work. How do you make sure that the machine gives you some results which are unbiased, correct, and they are not based on some false information and all that stuff? Machine has no idea, because it is not really intelligent in that sense. It doesn't have a conscience. Even we as human beings, we have conscience, still we make all kinds of mistakes, sometimes on purpose, sometimes we just don't, we are not even aware of. So that's one of the issues. Transparency is another issue. For example, if banking industry is trying to use some of these foundation models, some of these large language models to say give a loan to somebody, and they reject a loan to one XYZ businessman, that person can ask, why was my loan application rejected? And they might say, well, this is how the machine came up with an answer. You want to know what was the input given to the machine based on which these models predicted that, okay, I am not a good person to give a credit to. And that is one of the biggest issues with this, as to the transparency of the foundation models. Now, some companies like IBM, for example, it has its own Granite models, which are purely based on scientific data. Its input is not internet. Its input is scientific papers, its own research work, plus wherever they are trying to install it. Let's say they are trying to install it in a big bank, say Chase Bank. And so what they will do is, they will try to get the data from that bank's internal communications. And when they do that, then what happens is, you have what you call as your own proprietary information, and based on that you can have the models available which are much more reliable, and it's proprietary to you, and then you don't have to give it to some of your competitors, for example. And you have much more trust on that. You have transparency because you know what the inputs were. That can be told. So this is where things are headed. As a business value for AI, you really want a trustworthy AI, not the one which is trained based on internet data, for example. Slow lawmaking and regulations I have talked about earlier too. It's basically, politicians are much slower. Democracy is much harder thing to run. Some people agree on anything, and others don't agree on anything. To make a law takes a lot of time, and technology doesn't really wait for you. It keeps moving forward. So there is some need for governments to really be much more proactive in some of these things. One of the biggest challenges in AI today is that until now, we are still, human beings are still the biggest creator of the data. I mean, all the data in the world, the digital data that we see, the videos, the movies, the pictures, the images, we as human beings take those things and we put them in the internet, we put them online, or the text, the messaging, all this communication, whether it's WhatsApp or other text messages or emails, all of that is created by human beings, most of it. Machine created data is much little. Now imagine a time, Gartner did a study, they said by 2030, almost two-thirds of the data in the world will be generated by machines, not by humans. But remember how the machines are generating data. They are taking as an input human generated data and giving an output as a machine generated data, but that's never fully accurate. Let's say it's 70-80% accurate. Now that's the new machine data. For a next machine, that becomes the input, and that, let's say that next machine is also 80% efficient. So you have this 80% efficiency, the next one is also 80% efficient. So the second machine's output is probably 64%, 80% of 80%, 64% more reliable compared to what was the input. Now if you keep going this for a long time, it's what's called the entropy law, right? Over time you are actually losing information, and you are getting what you call as a kind of a garbage, kind of a hallucination. You think what you are getting is good information, but apparent maybe not. So that's something people need to think about. It is already being discussed, in the scientific community and technical community. People are looking into this, but there's something you need to keep in mind. Now, generative AI is one of the biggest, I would say, user of the computing power I told you earlier. But I also told you earlier that the semiconductor technology today is at 3 nanometer, pretty soon at 2 nanometer. And you might think even GPUs, not just CPUs, GPUs too, they all are based on silicon semiconductor. What happens when we are stuck now? We reach the limit on this, which is not going to be very far, maybe another 10 years, maybe. Semiconductor technology probably will come to an end. But your zeal or your requirement for computing power never goes off. So you want even more powerful computers, computers which can do computations much more faster, maybe even faster than GPUs, especially for AI kind of work, and something similar to AI. Where will you get those things? This is where quantum computing comes into picture. Now I'm transitioning from the AI into the quantum now. The quantum computing came into existence because we realized that a quantum system, those of you in physics now, this is a little bit of physics problem, I think, so I want people to really focus on that, physics students in general, that a quantum system can be in multiple states at the same time. We have what's called the concept of a wave function, which is a linear combination of multiple states that the system can be in. Now in general, a quantum system can be in a state like a billions of states at the same time with different probabilities, of course. You could use that feature of quantum systems to be in multiple states, and some other features of quantum, for example superposition principle or the teleportation idea of quantum. To do all of that, you could use that feature to actually convert that into a computing powerhouse. And this is where the idea of quantum computers became more useful in the AI community, because we realize that semiconductor is coming to the end. Quantum computers, even though for an individual task they may be slow as of today at least, compared to a processor which is runs in gigahertz, in quantum system run in maybe at the most megahertz processors, but a quantum system can be in billions of states at the same time. And especially when you have lots of qubits, if you have billions of states at the same time, then you probably can overtake any of the silicon based technologies, which is a qubit, which is a bit based ones and zeros. So let me describe to you a little bit about what the quantum systems are. Now a while ago, back in 1981, Richard Feynman actually said this earlier too, that nature generally is quantum mechanical. We know that at the basis of everything is atoms and molecules, they behave in a quantum mechanical way. And if you want to solve natural problems, for example, if you want to figure out drug interactions, you want to work in the areas of discovering new drugs for brain issues or maybe cancer or something else, you need to work in a system or in a machine which works at the quantum mechanical level, which can understand that. So think of it this way: if you have a problem which is exponential, and if your computing is linear, you will never catch up, even if you are faster in the beginning. An exponential curve goes much faster than a linear curve, however, even a polynomial. So you need a machine or a system which is itself inherently exponential in computing. Quantum systems are the exact example of that. They are exponential in nature. So if your problem is exponential, your computing is also exponential, you might be able to catch up and solve some of the biggest problems that we have. Molecular modeling, for example, think of it this way: so let's say you have a carbon tetrachloride, CCl4 molecule, lots of electrons in it. Electrons, they interact with each other. Those of you who work in physics and in spectroscopy, you know that the kind of number of energy levels that you have probably are unlimited, with the large number of electrons in them. To solve each of those energy levels, to solve these kind of systems, you will need a quantum computer. A classical computer will not be able to do that for you, even if you run this in a supercomputer. So that is one of the issues why the quantum push was there. And of course with the AI now, we obviously need that too. Now quantum computers cannot really solve every type of problem. They are designed for a specific class of problems to solve. Now they probably won't be, you don't want to use a quantum computer to run say 2 times 2 like a calculator. For that a classical computer actually much better, much faster, and much more cheaper. But if you have some other problems, like as I said earlier, molecular modeling or some those kind of systems, then you really need a quantum computing there. The basic of a quantum computer basically is, unlike a classical computer where you have bits, zeros and ones, in a quantum computers you have what's called qubits. So qubits are kind of a states in a quantum system, where it can be in a state 1 or a state 0. And for example, if you take an electron or take a magnet, for example, right? A magnet has a north or south pole. Electron is something like a magnet you can think of, and it has its own spin like a north south, and it can be either in spin up or spin down. We call them, let's say, state 1 or state 0. A qubit is a quantum bit which is a combination of these states. So, you can have state 0 or state 1 for a quantum system. So, unlike a classical computer, for example, will use very deterministic system, right. In classical system, think of it, a classical computer like this. You give a problem and you get the answer from a computer. You give the same problem again, you will get the same answer from the computer. You give the same problem to 20,000 other computers, you should get exactly the same answer. Otherwise, something is wrong with those computers. That is called a classical behavior. In a quantum system, you give the same problem to a quantum computer, you will get an answer. You give the same problem to the quantum computer next time, you may get a slightly different answer with different probabilities. Okay? So, you might think that what is the use of this? Well, there are many places where you need a statistical answer, not necessarily a definitive answer. For example, if I asked you what is your age, you always give me a statistical answer. You never give me exact age. You do not tell me I am 13 years, 5 months, 2 days, 20 hours, 3 minutes, 45 seconds, millisecond old. You always say I am 20-year-old or 21-year-old. The reason is, we know the rough answer is good enough. There are many class of problems in the world where you do not need an exact answer to these problems. In fact, most of the class of problems do not require exact answers. When you do not need them, then you use the quantum system, because they can give you that, but much faster, especially for the large class of problems. Quantum system is also like, it has some of these characteristics which are never there in classical. So, for example, this has a duality nature, the uncertainty principle in quantum mechanics. I am not going to go into some of those details, but a few things you do want to remember there is probabilistic nature of quantum system. In quantum mechanics, as I told you earlier, unlike classical system where it is deterministic, a quantum system is probabilistic. It gives you an answer based on the probability of a system, not on exactly where the system is. Another behavior is superposition. States can superpose with each other. So, that is another behavior a quantum system has. Now, based on all of these, there is an entanglement, there is an interference. These four ideas of quantum system, like probability, superposition, interference and entanglement, together these are used to create the world's quantum computers. So, qubit, for example, is as I told you earlier, qubit is designed by different techniques, trapped ions, neutral atoms, but IBM uses what is called the superconducting circuit qubits based on the niobium, aluminum and on silicon wafers. This is a Josephson junction here in the picture that you can see, and it uses the quantum tunneling phenomena to really create a qubit. Now, in general, you want more number of qubits, just like in a classical computer, you want more bits. Earlier, if you remember, we used to have 32-bit computers. Nowadays, we have 64-bit computers. Everybody uses 64-bit. Gone are the days of 32-bit. Why? Because 64-bit computer will have 2 to the power 64 number of addresses available. So, you can have now terabytes of hard disk and even tens of terabytes of hard disk. Similarly, in a quantum system, you have multiple qubits, not just one qubit, 2 qubits, but multiple qubits. And to have a really good, more powerful quantum computer compared to, let's say, supercomputer, you probably need thousands of qubits, not 64 or something, thousands of qubits. But already, for example, at IBM, we have something like 1100 plus qubit system already available. Now, one of the issues with the quantum system, there are something called a quantum noise, and there is something called quantum error. The quantum noise is these systems, the quantum systems are generally very difficult to control. Remember, we are working with really, like, for example, electrons. We know in quantum system electron has uncertainty principle, right? You can never figure out where the electron actually is. So, you need to have an interaction with the electron. But the problem is, once you interact with the electron, you have changed its state. So, there is this concept of you are not really seeing what you think you are seeing, because the moment you observe a system, you have disturbed the system. It is no longer in that state. Okay? So, but the problem is, how do you work with the system if you cannot really disturb, if you cannot touch it, you cannot observe it, then how do you get information out of it? And that is the beauty of all these things. Then in quantum computers, we work on creating those systems where we have a probabilistic nature of this. We can say, okay, statistically speaking or probability wise speaking, there are 90% chance of this being the actual output and 10% chance of the other things being the output, for example, right. So, the quantum noise comes from, say, this inherent nature of this uncertainty of the position, or in general uncertainty in energy, time, position for quantum system. There is also something called a decoherence issue, because if you have multiple quantum systems, for example, you have, let's say, 15 electron or 16 electron systems, to keep them in sync together is very difficult. A small interference from anywhere can really cause the whole system to fall into something which is out of control, and that's called decoherence. In fact, even if you don't do anything, because of the uncertainty and other things, it will always go into decoherence. The most stable quantum system that we have until recently, I would say a couple of years back, was about one which is, I think IBM has one which is about 100 something microseconds. Think of it like this: you have a computer today, quantum computer, which can be on for about 100 microseconds, which is 0.1 millisecond. That's it. Imagine if your laptop was on for 0.1 millisecond, you won't be able to do anything. But that itself is good enough to do lots of computation. It's already being used commercially in many places. But the goal of the scientists and engineers for quantum system is to create a quantum computer which has much longer decoherence time, means a time where for which it stays coherent, it stays in one state, for example. So we can work with that system, and that is something you need to continue working on. Now, the other issue is the vacuum fluctuations. This is a little bit technical, but the vacuum fluctuation essentially is, even when we have something called a vacuum, which means vacuum means something where there is nothing, there is no matter, there is no energy, there is nothing. Even there you can actually create particles and antiparticle pairs. This is the quantum phenomena. It goes out of your mind, but that actually happens, and they can create their own electron positron pairs, for example, for a very short period of time. You can violate the laws of conservation everywhere there for the short period of time, which is decided by the Heisenberg's uncertainty principle. All those effects, they create their own quantum noise. Some of this is impossible for as human beings to really stop, but then we have something called quantum error, where we can do something about. So quantum error is interaction of the quantum system with the environment. As I told you earlier, imagine if you have a room with a vacuum, and if there is even a single other electron there somewhere in this whole room, and I have just 2 electrons which are supposed to be my quantum qubits electrons, and if I have any other electron, it will interact with them. It will disturb the system, and the whole thing get destroyed. So that's something we can control. We can try to make even more and more refined machines which will take care of all of that. Quantum error correction becomes the most important issue. So today scientists, they talk about a quantum volume. A quantum volume is number of qubits should be high, but the quantum error rate has to be the lowest. So a machine which has the highest number of qubits with the lowest error rate has the highest quantum volume. That means that's the most powerful quantum computer you will have today. So this is a good graphical picture here just to show you these big boxes. The bigger the box is, the more quantum volume it has. It's essentially, it goes on to the left top, it goes to lower error rate, and to the right bottom it goes to the more qubits. So as I told you earlier, these days we have, this is IBM's quantum roadmap. By 2023, IBM had announced that they will have Condor, and you have, I think today we have about 1140 or some number of qubit systems available today. Again, we are still working on coherence time improvement and or decoherence time reduction, and we are also working on trying to improve the error rate. So the biggest game in the industry is how to create a system, a quantum system which is stable for a second, forget the minutes right now, even seconds. We are still in milliseconds is time scale, and to have as little quantum error as possible. We don't have to worry about the speed. As I told you, it's like these systems can really work in parallel, billions of states together. If you have 1000 qubits, you can imagine 2 to the power 1000 is the total number of states the system can be in. That's already more than 2 to the power 64 that you have the world's fastest supercomputer with. So that's already taken care of. The speed we don't have to worry about. What we have to worry about is the quantum error correction to make it better, and at the same time we have to worry about trying to reduce the or to increase the number of qubits being stable, meaning to improve the decoherence time. So this is one of the example of an actual commercial quantum computer qubit 1121 qubit system. This is Condor, IBM's system. Talk about just one more thing here. Quantum systems became reality about, I would say, maybe 5 years back or so, maybe 10 years back. Other companies are also working on this. They have their own different ways of doing quantum computing. One of the biggest issues and concerns people have around the world with quantum systems is this security implications. Because as I told you earlier, a quantum system can be in multiple states at the same time. So it can actually do Things like prime factorization. Let us say I gave you a big number. A big number means a number which has, let us say, 200 digits, that big a number, and all I told you it's a product of two prime numbers. Try to find out what are those two prime numbers. That's the simple question people have, and there is no algorithm today known which can actually solve this problem. There is no mathematical formula for prime numbers. We don't know how to solve this problem. The only way to do this is brute force. Try all combinations starting from the prime number 1 to whatever 3 and 5 and 7, and then keep going forever until you hit this. Well, classical computers will take about billions of years to really solve. Even a supercomputer will take billions of years to solve this problem. So, we are safe. But once you have a quantum computer ready and working on this, it can do all those billions of things at the same time. It can actually break the RSA encryption. RSA encryption is RSA were the three MIT scientists there, I think American scientists, Rivet, Sherman and Edelman, who actually created this encryption based on which your email works, your banking systems work, your everything, all your encryption, all your security systems work. This system is based on the simple prime number computations, prime factorization computation. And it turns out that a sufficiently powerful quantum computer with about 6,000 qubits with a very good error rate. So, not very good, I mean not much error, and stable enough for even a minute or two can break this RSA encryption. If that happens, this whole concept of passwords and everything is gone down the drain. It does not matter. Anybody who has a nefarious ideas can break the system and can get all your information. This has security implications for the governments, it has security implications for the banks, for anywhere, for individuals, for healthcare records, for just about anything in the world. And so, people need to be concerned, and this is some people are already thinking about in this direction. But this is a big threat that is coming in. In fact, there was a news recently about maybe a few weeks back I read that some of the scientists in China, they have created a quantum system which was able to break, I don't know, maybe not 256 bits RSA, but maybe a shorter version thereof. But if that is the case, we are not very far until somebody says, okay, we have today broken 256 bit RSA encryption, for example, which is what most of us use anyway. So, that is one of the issues. So, how do you solve this problem? Peter Shor, MIT scientist, he came up with this idea. It is called Shor's algorithm. He designed an algorithm. He says, well, if the quantum computers can actually do this, breaking of this thing, you can also probably create a quantum safe algorithm, so for encryption. So, there are two things. So, he said that actually you can convert, basically Peter Shor's idea was that you can convert a quantum system into a kind of a linear system, effectively speaking. So, it can solve those factorization problems, and it actually gave an algorithm how to do that. The problem is if it is used for RSA decryption, then we are in trouble. And today we have a lot of companies, they work on how to build quantum safe algorithms. One of the algorithms was designed by us. We created this, we have a patent on this, it is called the secure communication using multi-channel noise. And what we have done is essentially using a technique we have used in astrophysics called pulsar detection, where we use the effect of integration of pulsar signals to create a good signal to noise ratio. And that is technique. Those of you who want to go into detail, you can go through this patent, it is already there in Google right now. But this is one of the techniques you can use to secure yourself against quantum attack in the future. But there are also quantum based encryption techniques which a quantum system will not be able to break. So, those are also being worked on, where essentially your security will be in such a way that if any attacker ever tries to even read it, because reading is an observation, the act of observation will collapse the wave function, meaning the whole system will collapse and you will not get any information out of it. So, that is also being worked on. So, that is on one other technique. Ours is a classical technique, that is a quantum technique, but that is where we are. So, this is basically the end of my lecture today, and what I wanted to give you the rough idea about three things are happening together. Semiconductor technology is slowly reaching its peak. It's pretty soon, in a decade or so, it will be there, like it's no longer going to be based on semiconductor. What else can you do? So, you can continue building the chip, but you are stuck, like there are no technological innovations here anymore. AI requires a never ending demand for computing, and here is coming quantum computing, which says we have the capability to give you as much computing power as you need, provided you can reduce the error rate and you can increase the coherence time. And the challenge for everybody who is listening here, those who are budding scientists, budding engineers who want to spend some time, think about these, look into some of these problems, see what you can contribute. This is a quantum system is a very new technology. I would like our students in India to take this up as a challenge. Maybe come up with a newer your own ideas for security, for decoherence time reduction, or for to increase the coherence time, or to maybe create your own quantum systems. Electrons are not the only way. You can have photons, you can have something else. Any multi-state system can be used for quantum computing.